Assalamualaikum, hello, and welcome to our video presentation for assignment 3 of a learning factory. So we would like to thank you, Dr. Muhammad Ghazali bin Ma'ruf, for this opportunity, and we are from group 4, and we are consist of myself, Muhammad Nazmi bin Arifin. My metric number is PD 23024, and my teammates member are Nur Alia Fatahirah binti Muhammad Faizal, PD 23023, Nur Nisa Najla binti Ismail, PD 23026, Ahmad Fauzan bin Ahmad Faizal, PD 23025, and Haziq Shahmi bin Hassan, PD 23020. For this assignment, our task is to conduct a time study and line balancing study. Our specific production target is to achieve a total capacity of 900 pieces per day. To achieve this, we have analyzed the entire workflow, covering three critical stages: assembly, inspection, and packaging. The products we are focusing on today is the USB fan. Before we start the line, let's look the key components required for the assembly, which are the fan body and motor, the fan blade, the protective casing, the fan stand, and the packaging box. We have also designed a specific jig and Poka-Yoke system to ensure the assembly is smooth and error-free. So, how do we calculate the efficiency to meet the 900 unit target? I will pass this to Alia Tahira to explain our process flow and time study data.
Next, for this part, I will explain the process flow and time study for the USB fan assembly process. The first step is installing and tightening the fan motor, fan body. The observed cycle time for this task ranged from 29 to 32 seconds. This task was repeated a minimum of 5 times for the time study. Install fan blade. Next, the fan blade is installed and secure. The observed cycle times range from 19 to 21 seconds, repeated 5 times. Align and attach from guard to rear guard. Next, the fan blade is installed and secured. The observed cycle times range from 19 to 21 seconds, repeated 5 times. We will move to install the left and right stand. In the final assembly stage, The left stand is installed. The observed cycle time range from 34 to 37 seconds, repeated 5 times. Next, the right stand or base is installed. The observed cycle times range from 29 to 32 seconds, repeated 5 times. Next, functional inspection. After assembly, functional inspection is conducted to ensure the fan operates properly. Observed cycle times range from 29 to 32 seconds, repeated 5 times. Packaging into box. Finally, the USB fan is packed into the box. Observed cycle times range between 24 to 27 seconds, repeated 5 times.
Hello, and now it's the time for the takt time calculation. First, we calculate the takt time, which represents the maximum allowable time, where most typical factory, it operates around 8 hours. So that's the available time that we assume for our line balancing. And then 8 hours is equivalent to, if you multiply it by 60 and then multiply by 60 again to get seconds, so you get 28,800 seconds. Because as you know, 1 hour equivalent to 60 minutes and 1 minute equivalent to 60 seconds. So you have to multiply 60 twice in order to get 28,800 seconds. And then just as we have here the total capacity in a day, which equivalent to daily demand units required, you can see here, actually it's the same, it's here 900 pieces per day. You just have to compute these two values into the formula. So we have 28,800 seconds divided by 900 pieces per day. This is for the takt time. Hence, we get the answer, which is 32 seconds for a unit. 32 seconds per unit. This means the production line must complete one USB fan every 32 seconds to meet daily demand. Next, we calculate the standard work in process, or in abbreviation known as SWIP. So SWIP indicates the ideal number of units that should be present in the system to maintain a smooth and continuous production flow without excessive waiting or congestions. So the formula of SWIP, as you can see on the screen, is total cycle time divided by takt time. And takt time previously we have calculated, and it is 32 seconds per unit. So we just compute the value here. First, 32 seconds per unit. As for the total cycle time, we take it as 243 seconds. This is actually the value of standard time, where we get it from by calculating the average time first, and then the normal time, and then the total normal time, and then standard time, by dividing total normal time by 1 minus allowance factor, and we get 243 seconds. Before we've calculated, we compute this in the calculator, and we get the answer 7.59 units. Since WIP, which is work in process, must be a whole number, we round it up as 8 units. So this means that 8 units of work in process are required across the production line to ensure continuous flow and prevent and determine the minimum number of workstations required for the assembly line. This calculation ensures that the production line can meet the takt time without overloading any workstation. So the formula, as you can see here, the minimum workstation is equals to total normal time divided by takt time. Why total normal time instead of standard time, ST, that we've calculated earlier for the SWIP? We're using SWIP because, line balancing focuses on the actual work content without considering allowances. So the standard time, we've included the allowance factor, but the total normal time, we just calculated the total of each normal time of each process steps. So as we already have the takt time value, we just put it inside the formula and substitute into the formula. So the takt time is equals to 32 seconds per unit. Alright, per unit. As for the total normal time that we have obtained from the calculations previously, it is 206.64 seconds. Together, we key in these figures into the calculator, and we get 6.46. It is actually not. We must make sure that since it's not possible to have fraction of a workstation, so we have to round up the value into 7 workstations. Therefore, at least 7 workstations are required to meet the production demand. So all these together, these calculations, ensure that assembly line is efficient, balanced, and capable of meeting daily production targets with minimal waste, and our daily production target is 900 pieces per day. Thank you.
Hello, my name is Haziq Shami. So this slide shows the precedence diagram for the USB fan assembly process. The tasks are arranged sequentially from activity A until activity G, starting with tightening the fan body and ending with the packaging. Each task must be completed before the next task can begin, because every assembly process depends on the previous one. For example, the fan blade can only be installed after the fan body is properly tightened, and the inspection process can only be performed after all assembly components are complete. By using the precedence diagram, we are able to clearly identify the correct task sequence and understand the dependency between each process. This helps ensure that the assembly flow is logical, systematic, and consistent with the actual production process. So for the line balancing, the takt time for this production line is 32 seconds per unit, which is determined based on the required production output. Using the total task time from the time study, the minimum number of workstations required is 7. Therefore, the assembly tasks are distributed into 7 workstations according to their precedence, order, and standard time. Tasks with longer processing times are assigned to separate workstations to avoid bottlenecks, while shorter tasks are placed appropriately to maintain balance across the line. This line balancing approach helps reduce waiting time between workstations, improve production flow, and ensure that assembly line can consistently meet the production target efficiently.
Poka-Yoke. What is Poka-Yoke? It is a method used to prevent human error during a process before defect happen, instead of detecting them after. Before using a JIT, the operator aligns the part manually. This can cause misalignment and incorrect assembly. Incorrect positioning may lead to loose part, rework and product defect. So, to prevent this issue, a JIT is introduced as a Poka-Yoke solution. The JIT holds the component in the correct position. This is allowing assembly in only one orientation. This prevents misalignment, reduce error and improve the consistency, and also speed up the assembly process. In this part, screws are placed loosely on the working table without any proper organization. Because the screws are not separated, they can easily fall, get mixed up, or be mistaken selected during assembly. This situation increases the risk of using the wrong screw size, which can cause loose assembly, damaged component and rework. To prevent this problem, a compartment tray is introduced as Poka-Yoke solution. Each compartment is designated for a specific screw type or size, it ensuring the screws are properly organized and easily identifiable. The operator only pick the correct screw from the correct compartment, so it reducing the possibility of screw mix-up. This is a prevention Poka-Yoke. It's focused on eliminating the cause of error by organizing components in a way that makes mistake unlikely. This method prevents error before they occur. Rather than detecting them after assembly, it does not depend on the operator memory or experience. Instead, the process design itself helps guide the operator to perform the task correctly.